Okay, so we have to finish up 6.1. By the way, the audio on the previous videos was not working on Monday's videos, so they're less exciting than the usual videos. Just so you know. So I had to close this, but remember that we had solved for what the gain was from the magnitude criterion, right? Big K equal to 1 over the magnitude of G of S, H of S. And so we did that before. And we also were trying to come up with this geometric gain as well. So remember, we know how to evaluate functions. This GH is a transfer function, any complex function. We know how to evaluate them at a point S, so S equals psi, a test point. And we know that in the case of finding just the magnitude, we can take the magnitudes of the distance from each of the open loop holes and zeros to the test point and divide and multiply them. So the formula that we came up with was the product over all the j's of it was P, was it psi minus Pj or?
Psi minus Pj.
Okay, yeah. Psi minus Pj, and then divided by the magnitude of little k, which comes from GH. So GH is, of course, composed of a bunch of poles and zeros, right? So I'll just do an example here. Maybe 3 times S plus 1, and then S plus 2, and then S plus 4 or something. Remember that, so the poles and zeros describe all of this transfer function with the exception of 3, right? That little constant out there. That's what we're calling little k here. So little k, magnitude, product over all of the psi minus zeros. Oh, and these were lengths, right? Yeah. Take the length of each one. Okay, so this is these are the two expressions, and I want to unpack this later one here for just a minute. 6.3. So this figure should give you a sort of an example picture of it. So here are our, here's an open loop pole, here's another open loop pole, here's another open loop pole, and here is an open loop 0. So we know that our locus is going to start at these open loop poles and go to open loop zeros, one of which is finite, 2 of which are at infinity, right? And if we want to evaluate k, big K, equals 1 over magnitude of G of S, H of S, one way to do this for psi's that show up, test points that show up on the locus, one way to do this is to take vectors that originate at each of these open loop poles and zeros and terminate at psi, our test point, find the lengths of each of them and plug it into this formula here, which is the one that we drew up here, 6.3, for this specific example. So the blue ones are the pole ones, so the pole lengths. Take the product of all the pole lengths divided by the product of all the zero lengths, which is only 1 in this case. And then in this example, I didn't give a value for k, but if there's no value given, you can just assume it's 1. So that's the geometric interpretation. And it works well if you're trying to just do this by hand, and it gives you kind of a feel if you move this around. So if you're making, there are 3 pole vectors and 1 0 vector in this case. So as you increase the gain here, you're moving along this line in this direction here. And you can see that since there are 3 poles and they're in the numerator, as you move this farther and farther away, the lengths all approach each other, right? Except that the numerator's got 3 of them. So it's just going to increase more than the one that than the 0. So that's why we have this gain going to infinity as you go along this line, because the numerator poles, you can think of it as being the numerator poles, have length to the test point that gets larger and larger, and there are 3 of them. They're in the numerator, so that's why it goes off. That could be balanced out if we had more zeros. And then if it was balanced out to the point where you had as many zeros as poles, you wouldn't have any zeros at infinity, right? You would have only finite zeros, in which case you wouldn't have this explosion in gain as you go off, increasing gain to infinity. You wouldn't have this explosion in the 0 location. So this is, I mean, you can think about it in different ways. I'm trying to kind of give you guys an alternative way to think about it to improve your intuition about the root locus, and then also to give you a way to solve for the gain geometrically. So if you're given a pole 0 plot and you're given a test point, say that matched some design criterion like a certain rise time or a certain percent overshoot, you knew you wanted your closed loop poles to be here at this location, then you could draw vectors from all your open loop poles and zeros to that point, find the lengths of those vectors, and then figure out what gain would be required to make it happen. So not super useful when you're sitting around with MATLAB, because in MATLAB you don't have to do this. But if you are just, looking at a graph with a root locus on it and you need to decide how much gain, that gives you one way to find it. And I think it's useful on an exam because I think in this class we're going to have an in-class final exam. So you got to be able to do something by hand with this. You
say going up right there, is that little k gain or is that big K?
It's this? Yeah, this is big K.
So big K is gain, but little k is gain, correct? Not big K.
So they're both, we call them both gain sometimes, so it's a little, you have to be a little careful. So the big K is the gain that we're going to put in the controller block. So we have a feedback controller. Little k is the gain that's inside the plant. And in fact, it's the whole open loop gain. But if you said little k g, well, it's not really fair to say that. So it's your plant has a k in it, little k, and it's got the zeros, and it's got the poles. It's the little gain that's out front. If you were to take your G and H and find a gain in there, that's your little k.
So little k is gain, while big K is your gain.
Is your controller gain? Okay. Yeah. So the little k is something we don't have any control over. Little k is something that just comes from the plant. So if you've got a plant that's got some multiplicative factor out front of it for what it does. So say you put in a force of 10 newtons and you get out something that has a magnitude of 20 volts, then you have 2 volts per newton gain in the plant.
So you're saying, sorry, so we don't have control of the plant, we don't have control of the okay.
Yeah, so that's why we can't just use, If we had control over little k, we could just use it for the controller gain. But since we don't, we have to supply our own controller gain, which we have complete control over. We can set it to 0, to 25, whatever we want. Just to name a few, we could go on. We'd be here all day. So that's the idea with this gain. So we're trying to find the gain big K that corresponds to closed loop pole locations that have the properties we want, that have the performance criteria that we want. So there's an easier way. So there's the way, the geometric way. There's also just the analytic way of just plugging in your test value here, algebraically, just finding what the value is. So taking the magnitudes, just using our typical analytic plug and chug, right? There's the geometric way, thinking about lengths of vectors to the test point. So those are the 6.2 and 6.3 ways. And then there's the MATLAB way, or as I call it, the easy way. So finding the loop gain K that yields a closed loop pole at a specific point on the root locus is much easier to find numerically. Recall that for a given value of gain K, the closed loop poles are easily found numerically. Software typically generates root locus plots in a brute force way by simply computing the closed loop pole locations for a range of gains. So it does that. It finds the poles. It finds the roots of the denominator of the closed loop transfer function for each value of gain. So just like picks gain equals 0, finds it. Takes gain equal 0.1, finds that. Gain equal 0.2, finds that. So it does that. And in MATLAB, we already kind of went over this a little bit when we were just generating root locus, but I just wanted to sort of reiterate. This is the easy way. So most of the time, this is what you're going to use to find the gain. You have to recognize how to find it analytically or geometrically too. So we're going to do a design problem with MATLAB in the next lecture, so I'm going to expand on doing it with the MATLAB, the easy way, in that lecture. Okay? Any questions before we move on to an actual design problem? Okay. Oh, there was a question.
That gain is the same as if your location were on the other side of that. So the two poles that are complex conjugates, if the point were on the other side of the locus at the same spot, right? So just like straight down.
Ah, here?
Yeah, the gain is the exact same.
Yeah, exactly. So this corresponds to one of the poles. It also, so there are 3 poles, right? So whenever the gain is whatever it is at this point, so say the gain's 5 to get that test point, there's a closed loop pole here. There's also a closed loop pole straight down here too. And then there's also a closed loop pole somewhere in here, right? So each branch of the locus has a closed loop pole there for that gain. You can choose any of them. They're going to give you the same gain. So you could choose this one or this one or this one, whichever you want to find the gain from. And you could draw your vector lengths to there. So it's satisfied for each of the 3 closed loop poles in this case. The reason why we would typically take one of the complex conjugate pairs as the test point is that we're typically trying to remember if we have a conjugate pole pair that's closest to the imaginary axis and the others are further away, then there will be it'll be approximately a second order system dominated by that conjugate pole pair, and then we can make assumptions about relationships like rise time and settling time and all that, percent overshoot. So that was back when we derived that in the transient response characteristics, the performance. We talked about rise time and settling time. All had to do with, analytically, we could find that with the closed loop pole locations, as long as the second order system dominated. So, and we'll do that in actually, so this very next this example that we're going to do, I think this will become a little bit more clear. So, yeah, but I think you're on the right track. You're right, there is more than one. The same gain will correspond if you choose any of those points, any of those 3 points. It's easiest to see when you talk about this one down here, the pole lengths divided by the zero lengths. It's just sort of a symmetric problem. The other one's a little harder to see.